Hello everyone. Today we continue on chapter 4, mining data streams. As we know, the data streams is actually kind of unstopping data streams. So in chapter 4, we concentrate on dealing with infinite data streams. The typical algorithm, we are focusing on the data string filtering and the queries on strings, and also regarding the web advertising strings. As to the data streams, which happens in many data mining situations, which means that we do not know the entire data set in advance. The data just coming unstoppably. Well, the stream management is also important when the input rate is controlled externally. For example, the Google queries and also the Twitter and Facebook status of updates. All such information are really unstoppable, so we can think of the data as infinite and non-stationary. In other words, the distribution changes over time, from time to time. Most of these algorithms described in this chapter assume that we are mining unlimited database, so all of data is sometimes unpredictable from its new assumption that data arrives in a string or streams, and if there is not processed immediately or stored, then it is lost forever. Moreover, we shall assume that the data arrives so rapidly that it is not feasible to store the data in active storage. For example, the data cannot be stored in conventional database. So the interaction with the data is really the time of our choosing. So the algorithm for processing such streams involves summarization of this string in some way. We shall start by considering how to make a useful sample of a string and how to filter a string to eliminate most of the undesirable elements. And later on, we will show how to estimate the number of different elements in a string using much less storage than what is required if we list all the elements we have seen. Another optional approach for summarizing a string is to look at only a fixed length window, like a slider window, consisting of the last n elements for some reason. We then will query this window as it was a relation in the database. If there are many streams and we may not be able to store the entire window data for every string, so we need to summarize even the windows. So all these fundamental problems will be addressed in this chapter, and maintaining an approximate count of number so as to use less space to store the entire window itself. So okay, let's begin with discussing the elements of strings and the string processings. The difference between streams and databases and the special problems that arise when dealing with the streams. Some typical applications where the stream model might be should be examined. Now, so what if a system cannot store the entire string accessibly. So the question would be, how do you make critical critical calculations about the string using a limited amount of secondary memory? So this is a general string processing model. In an analogy to a database management, the string processor is a kind of data management system. The high-level organization can be illustrated in this figure. Any number of streams can enter this system. Each stream can provide elements at its own schedule. They need not have to have the same data rate or data types, and the time between elements or one stream need not to be uniform. So the fact is that the rate of arrival of string elements is not under the control or under any estimation of the system, which distinguishes string processing from the processing data that goes on within a database management system. So anyway, in a word, it's totally different from the conventional data system. Well, the latter system controls the rate at which data is read from the disk, so therefore never has to worry about the data getting lost or as it's time to execute the queries. As we can see from this figure, streams may be arrived in a large archival store, but we assume it's not possible to answer queries from the archival store. It will be examined only under special circumstances with time-consuming retrieval processes. There is also called a working store, into which summaries or part of the strings may be placed and which can be used for answering queries. The working store might be a disk or it might be main memory, depending on how fast we need to process queries. But either way, it's of sufficiently limited capacity that it cannot store all the data from all the strings. The problem caused by such kind of data stream is that the types of queries one wants to answer on the data stream. For example, how to sampling data from a string, whether is it applicable to construct a random sampling strategy. And the second is that how to construct queries over sliding windows, which means that the number of items of type X in the latest k elements of a string, how to implement such query in the window is also quite challenging issues to deal with such kind of data streams. And the other problem, and also including how to filtering a data string, since the data string is unpredictable and unstoppable and indefinite and infinite, so how to select elements with a property from this string is also another very important issue to be stated. And the fourth is how can we count distinct elements with the limitation of the window size, so that the number of distinct elements in the last k elements of the string. And the next would be how can we estimate the moments. The moment means that how can we estimate the average value standard deviation of the latest elements, and maybe applies to the later or other statistics analysis. And the last issue would be how can we find frequent elements with the data string. We still need to find the frequent elements based on the whole data string. As to the specific applications regarding the data string, the first would be how can we mining query strings. As we know, all the search engines want to know what queries are more frequent today rather than yesterday for the prediction of the user input. For example, the Google receives hundreds millions search queries per day, while Yahoo accepts billions of clicks per day on their various sites. Many interesting things can be learned from these streams. And for example, an increase in queries like a sore throat enables us to track the spread of virus, and a sudden increase of a click rate for a link could indicate some news connected to that page, or it would mean that the link is broken and needs to be repaired. And together, the social network news feed will also can be used to track the topic development trends on Twitter and Facebook as well. So all the threes belongs to the internet and web traffic analysis. There are also other applications regarding in the data stream. The first is the sensor data from the sensor networks, because many sensors are feeding information to the central controller. For example, if a temperature sensor bobbing about the ocean, sending back a base station reading the surface temperature each hour, the data produced by the sensor is a string of real numbers. It's not a very interesting string, since the data rate is so slow it wouldn't stress modern technology, and the entire string could be kept in my memory essentially forever. But for now, if you are given a sensor of GPS unit, let's say it reports the surface height instead of temperature, the surface height varies quite rapidly compared with the temperature. So we might have the sensor send back a reading every tenth of a second. If it sends 4-byte real number each time, then it will produce 3.5 megabytes per day. It will still take some time to fill up the memory, let alone a single disk. But one sensor might not be that interesting to learn something about the ocean behavior, or a much larger area. We might want to deploy a million sensors, each sending back a string at the rate of 10 per second. So a million sensors isn't very many, but it would be one for every 150 square miles ocean. So we will have 3.5 terabyte arriving every day. So that is a huge number. Okay. And also including the telephone calls, because we have so many mobile calls through the communication network. The data feeds into the customer bills as well as the settlement between the telephone companies as well. And also in the web and the network, all the IP packets are monitored at a switch, and the switch will gather all the information from the different end node, so as to optimize the routing, and also how to detect the denial of service attacks. And beyond this PowerPoint, we also can have some other applications like image data collections from the satellite. As we explore the Earth with the satellite, which take photos from the space. The surveillance cameras also produce images with lower resolution than the satellite, but there are so many surveillance cameras of them. So altogether, they are producing a stream of images at fixed intervals for fixed seconds. Okay. So regarding the string processing, there are a few issues we need to be addressed. Before we discuss the algorithms, the constraints under which we work when we dealing with the streams. The first is that the streams often deliver elements very rapidly. We must process elements in real time, or we could lose the opportunity to process them at all. Without processing the archival storage, it's often important that the string processing algorithm is executed in main memory. Without access to secondary storage, or with only rare access to the secondary storage. Moreover, even when streams are slow, as in the sensor data applications, there may be many other streams, even if each stream by itself can be processed using a small amount of main memory. The requirements of all the streams together can easily exceed the amount of available memory instantly. So many problems about stream data could be easily solved if we have enough memory, but become rather hard and require the invention of new techniques in order to execute the algorithm at a realistic rate on a machine of realistic size. Here are some general thoughts about the stream algorithm worth bearing in mind. Is that the first thing, it is much more efficient to get an approximate answer to the problem rather than an exact solution. The second is that a variety of techniques related to the hashing turned out to be useful. So generally, these techniques introduce useful randomness into the algorithm behavior in order to produce an approximate answer that is very close to the true results. Okay. So next, we are moving on to the very practical operational issue, sampling. How can we sampling from a data string? The first thought would be we can sampling a fixed proportion. As the stream grows, the sample will also get bigger. So this is might be a very important issue caused by this kind of sampling strategies. As we know, when we're dealing with data streams, since we cannot store the entire data string, so one obvious approach is to store a sample. There are two different thoughts regarding this problem. The first one is that we can sample a fixed proportion of elements in the data string. Say we can sample 1 in 10. Second is that how we can also maintain a random sampling strategy of a fixed size over potentially infinite string, which means that at any time k, we would like to using the random sample of S elements. This is the property of the sample we can maintain for all the time steps. Each k of k elements seems so far as equal to the probability of being sampled. A general problem we may address here is that we can also selecting a subset of a string so that we can ask queries about the selected subset and have the answers might be statistically representative of the string as a whole part. If we know what queries are to be asked, then there are a number of methods that might work. But we are looking for a technique that will allow ad hoc queries on a sample. Okay, so our running example is like the following issues. A search engine receives a string of queries and it would like to study the behavior of typical users. We assume the stream consists of tuples which are composing the user query and time. Suppose that we want to answer the queries like what fraction of the typical user's queries were repeated over the past months. Assume that we wish to store only 10% of this stream, so probably this kind of sampling with portion would be a very applicable thought regarding these scenarios. Like I said, sampling with a fixed proportion, which applies to the data coming evenly and distributed scenarios. Okay. So the very obvious approach would be to generate a random number from 0 to 9, which responds to each search query. Store this tuple if and only if the random number is 0. If we do so, each user will have average 1/10 of their queries stored. So the statistic fluctuations will introduce some noise into the data. And if the user issue many queries, the law of large numbers will assume that the most users will have a fraction quite close to the 1/10 to their queries stored. However, this scheme gives us the wrong answer to the query asking for the average number of duplicate queries for user. If suppose the user has issued a search queries one time in the past months, maybe D search queries twice and no search queries about the twice. So we probably have a 1/10 sample on queries. So the problem with the naive approach is that we cannot define what fraction of the queries by an average search engine user are duplicates. So this is a kind of issue. How can we address the S queries once and the D queries twice? So the correct answer would be the D divided by X plus D. Suppose we have such a solution, we will keep 10% of these queries. Sampling will contains X divided by 10 of the singleton queries and 2D divided by 10 of the duplicate queries at a time. So in that case, only D divided by 100 pairs of the duplicates are stored and or sampled. So in that case, of the D duplicates, that's 18D divided by 100 appears exactly once. So the sample-based answer would be the D divided by 10 times X and 19 times D. So which is quite different from the correct answer itself. So in that case, the sampling frequency and sampling position has quite big errors regarding the compared with the correct answers. So how can we solve such problems? The solutions might be we can use to sample users. We can do sample users. We can pick. In other words, we are not sampling queries. We are sampling users. We can pick about 1/10 of the users and take all their searches in the sample. And also we use a hash function that hashes the username and the user ID uniformly into 10 buckets. Thus, we can strive to pick 1/10 of the users and take all their searches for the sample, while taking none of their searches from other users. So if we can store a list of all users and whether or not they are in the sample, then we could do the following each time. A search query arrives in a string. We look up the user to see whether or not they are in the sample. If they are, we added this search query to the sample. If not, then we do not add it in the sample. However, if we have no records of ever having seen this user before, then we will generate a random integer between 0 and 9. If the number is 0, we will add this user to our list with a value in, and if the number is other than 0, we will add the user with the value out. So this is a general thought about sampling with queries and also with users. So if we illustrate such a solution in a more general manner, we can think about the stream of tuples contains with specified keys. The key is some subset of each tuple's component. For example, as we mentioned before, the tuple including the user, the search query keywords, and the searching time, and the key would be the user ID. So the choice of a key depends really on the real web application. To get a sample of A divided by D fraction of this string, we can hash each tuple's key uniformly into B buckets. So in that case, if the tuple is picked up for its hash value is at most A. So in that case, the B bucket will have the tuple in according to these queries as well. So here is the question I would advise you to think about. How can we generate a 30% a sample? Right. How about hashing into the B equals 210 bucket and take the tuple if it hashes into one of the first 3 buckets? Is that reasonable and applicable? And another methodology is that the queries can be applied over a quite long sliding window. As we know, the sliding window is a useful model to in stream processing. Is that the queries are about a window of length n. The n will cover the most recent elements received by the in a query. So the interesting case is that the n is so large and the data cannot be stored in the memory or even on a disk. Therefore, so many streams that Windows for cannot be stored. Well, if we take the Amazon as an example, is that for every product X, we keep the 0 or 1 streams of whether that product was sold in the nth transaction. if we try to answer these queries, how many times have we sold X in the last K sales? So the sliding window for one string can be illustrated like in this image. In this figure, in this image, we notice that the length of the windows is the size is n equals to 6. So the window is moving from the left hand to the right hand, which presents the past and the future data string with a fixed size. Okay. So with the fixed window, we can count the bits in the string. So the ones we collected from the string will be prepared to answer the queries in these forms. For example, like how many ones are in the last K bits. So the obvious solution is that we can store the most recent n bits. When the new bits come in, we discard the n plus 1 bits. We keep the window size in a fixed length. Obviously, you cannot get an exact answer without storing the entire window. So the real problem is that what if we cannot afford to store the n bits? Suppose n equals to 1 billion or even 1 trillion, which exceeds the memory that we can afford. So in this case, the question would be: Are we happy? Are we going to be happy with an approximate answer in these scenarios? So a general attemptation to this question is that we can count the ones in the last n bits, as long as the assumption is of the uniformity. In that case, we also can maintain two counters. The one is S counts the number of ones from the beginning of the string, and the Z counts the number of zeros from the beginning of the string. So we can easily calculate that how many ones are in the last n bits with the n times S divided by S plus Z. So what about if the string is not such a uniform string? For example, what if the distribution changes over time? So here comes the DGI method. This solution does not require the assumption of uniformity. This method will store the order of log n square bits per strings. So the solution gives approximate answer never off by more than 50%. The error factors can be reduced to any fraction above 0 with more complicated algorithm and proportionally store more bits. So the idea is that using the exponential windows, the idea is that might not be always working, but the solution is that we can summarize the exponentially increasing regions of the string, looking backwards, from the present to the past. Okay, so that we can maintain the fixed number of windows, we can drop small regions if they begin at the same point as the larger the larger region. So in this image is that we are maintaining two different windows here, and we have 0 and 1s, and above that we maintain the 0 and 1s, so we can combine the two windows into a longer windows to accumulate the 0s and 1s in these larger windows here. So actually, when we are maintaining a larger window here, which only records the ones numbers in this fixed window. Okay, so the windows, the number of windows is fixed, but the length can be exponentially increased to reduce the number of storage used to record the zeros and ones. So the idea is good. So what is the good in the other aspect regarding the practical implementation? As far as we know, the information we store is only order of log n square bits, because we can get the order of log n counts of logger with the bottom 2 bits each. And each update adds more bits enter errors in count no greater than the number of the ones is the unknown areas. Nothing's perfect, so what is not so good? As long as the ones are fairly evenly distributed, the error due to the unknown region is small, no more than 50%, but it could be that all the ones are in the unknown area at the end. In this case, the error is unbounded. So in other words, these algorithms need to be optimized or fixed up. Now, this is the fixed up version about the DGM method. The idea is that instead of summarizing a fixed length block, we can summarize block with specific number of ones. Let the block size increase exponentially, then there are few ones in this window. The block size stays small, so the errors are small. In the meantime, also we added a bit in the string to record the timestamp. The timestamps are recorded in the module n, so that we can represent every relevant timestamp in order of log n bits. The DGM method also including the bucket. The bucket is a record consisting, as we know that, including the timestamp at the end, and also the number of zeros between its beginning and end in a fixed window length. The constraints on the bucket is that the number of ones must be a power of 2, like 2, 4, 8, 16, etc. So that explains the order of log n in B is above. In that for how can we representing a string by a bucket? Either one or two buckets with the same power of two number is ones. Bucket do not overlap with timestamps, and also bucket are sorted by the size. The early appeared bucket are no smaller than the later buckets as the windows are increased from this moment and increased exponentially backwards. In the meantime, the bucket will disappear when their n-time exceeds the n-time unit in the past as well. So here is an example of bucketized string. In this figure, we first build up two windows of size 1. So there are three properties of each bucket that are maintained. Either one or two buckets with the same power of two number of ones, and the bucket do not overlap in timestamps, and also the bucket are sorted by the size. Okay, so in that case, the bucket are increased exponentially in order to record all the ones in the window. Once the ones in the fixed bucket exceeds the 80%, the windows will be increased exponentially of 2. Okay. So this is the bucket string. Start from the right hand to the left hand. And the information in the bucket is updated from time to time. When the new bit comes in, the last of the oldest bucket of its n-time is prior to the n-time unit before the current time. In the two cases, the current bit is 0 and 01, and if the current bit is 0, no other changes are needed. If the current bit is 1, so we need to create a new bucket of size 1 for just this bit, and we will also set up the timestamp in this bucket with the current time. If there are 3 buckets of size 1, we can also combine the oldest 2 into the bucket of size 2. If there are now 3 buckets of size 2, we shall combine the oldest 2 into the buckets of size 4, and so on. So that's how the windows are increased exponentially according to the size of the size 2. Okay, so here is a more dedicated example how we updated the bucket with the number of size. So since the current state of this string are like this, so first we count the ones of zeros. So the bit of zeros comes. The ones coming in from the right hand as the left present the past. Okay, so we got the two orange bucket just merged because we got three orange bucket here, so we need to merge these two into the yellow one. So when the next new bits arrival, so there is also a new orange coming. So then the zeros come. We don't need to create a bucket. So and another one comes in. So as to we need to increase a new bucket as well, so that we also merge the three orange bucket into two. Okay, so as a final result, the state of the bucket after merging will turn out into this phenomenon, like we every color of windows we only can every size of the bucket we can only maintain two we maintain the number of two buckets. So for now we have present how we using the bucket to record the number of ones to for query, and how can we implement and issue the queries to get from the data stream. First, we need to estimate the number of ones in the most recent n bits. We will sum the sizes of all buckets, but the last, and also we will add half the size of the last bucket. But we do have to bear in mind that we do not know how many ones of the last bucket are still within the wanted window. Okay, so if we go back to the example of bucketized string, we will notice that the string is still maintains the two of the size 1 and one size of 2, and for any window for any size, the number of windows cannot exceed the 2. Once the number exceeds the 2, the combination of windows should be implemented. Okay. Okay, here is some proof how the arrow bound is about 50%. Okay. Suppose the last bucket has a size of 2 of power r, then by assuming that 2 power with power r minus 1, and it's about half. It's about half of the size 2 without power r. All its ones are still within this window. We make an arrow of at most 2 with power r minus 1. Okay, since there is at least one bucket of each the size less than 2 of power r, so the true sum is at least from the sigma 1 and 2 and 4 and 2 with 2 of power r minus 1. So this is finally the sum up equals to the 2 of power r and minus 1. So the arrows are at most 50%. At 50%. So this is a very simple arrow bound proof, right? So another issue is that how can we further reducing the arrow to a smaller scale? How about instead of maintaining 1 of 2 for each size bucket, we shall allow the either r minus 1 or r buckets if r exceeds 2. Except for the largest size of bucket, we can have any number between 1 and r of those. So the arrow is at most at order of r minus divided by r. So once the r is picked appropriately, we can trade off the number of bits we store and also in the arrows. Okay. So here is some extension sorts. Here is some extension sort we can regarding the windows and arrows. Can we use the same trick to answer the queries how many ones in the last k, where k smaller than n? The answer is that we can find the earliest bucket B that overlaps with k. Number of the ones is the sum of the sizes of more recent buckets plus half size of B. So this conclusion can be easily explained in the fixed Windows image below. And another thought is that can we handle the case where the string is not bits but integers, which means that the string is not bits but integers, and we want the sum of the last element of integers. So the thought is that once we got the string of positive integers, we want the sum of the latest k integers. We, for example, the Amazon are using such kind of technology to calculate the average price of the last k sales. So the possible solution is that if you know all that have the most m bits, we will treat m bits of each integer as a separate string. We will using the DGM methods to count the ones in each integer, while the CI is the estimated account for the ith bits, and the sum is a sigma from I equals to 0 to I minus 1 of Ci and 2 power I. So the bucket is still can be used to keep partial sums. The sum, which means that the sums of element in size B bucket is at most 2 with 2 of power B. So if we sum in each bucket at the most of 2 power B, so we can get this illustration in these slides, that we can get this sample at here. So as a summary regarding the first half of the chapter 4, we can get the following conclusions: that sampling a fixed proportion of a data string, the sample size grows as the string grows, because we need to maintain a fixed window number rather than an increasing window number to record the ones. And the sampling can be applied with a fixed size sample using the reservoir sampling, and we can also using the fixed windows to count the number of the ones in the last n elements. Although the windows are designed the window size are designed to increase exponentially to hold more records in the ones, and also these methods can also be optimized with a few extensions. For example, the number of the ones in any last k elements can be recorded to produce the to support a constant queries, and also the sum of integers in the last n elements will be can also be calculated to as a total accounting of all the latest numbers as well. Okay. So this is the first half of the lecture regarding the chapter 4. So we shall using another lecture to cover the other half of the chapter 4. Okay, it's good for now. Okay, thank you everyone.